Next, Killian will talk about transport security in Tor browser, and the screen will come up with no problems. All right, amazing.
Hi everyone, I'm Killian, and I'll be talking about our protocol CoStricTor, which is about providing HSTS for Tor browser. And this is work I did with my colleagues Dan, Duncan, and Stephen. So HSTS, you may or may not know what it is. It's a HTTP header that a web server can set on your browser locally, and it says basically whenever you subsequently visit this website, you should only connect via HTTPS. Don't allow any insecure connections, and this is obviously great for avoiding sort of man-in-the-middle attacks and SSL downgrade attacks and things like this. But one issue is that it can be used for tracking. So any kind of malicious website can set a whole bunch of different source URLs and selectively activate HSTS on these URLs. And this can be sort of used as a unique identifier when you subsequently visit the website, which is not great. And so for this reason, Tor browser has always disabled HSTS, which prevents the tracking, but obviously then we lose out on that security guarantee. And this is particularly important in Tor because of the power that the Tor exit node has. You know, they have a particular ability to perform SSL stripping attacks or SSL downgrade attacks. And this is something that has been kind of seen in the wild. There's been attacks in 2020 widespread where people lost cryptocurrencies and things like this. So it's an important property that we're missing out on, basically. So our CoStricTor protocol is basically an attempt to actually crowdsource HSTS data amongst all different users of Tor browser, and that would mean effectively that everyone is sharing the same HSTS data, and so they can't be tracked because it's exactly the same. So this is a protocol we made from an adaptation of Rapport, which you may have heard Hamed talk about earlier, which is a privacy-preserving data aggregation algorithm that uses Bloom filters. And so I'll briefly discuss Bloom filters because it's all made of that. So it's a set data structure that consists of a fixed length bit string basically, and you can insert into the set and you can query membership of the set. To insert into the set, you can basically hash the string of the URL that we want to insert to say that it has HSTS. That'll give us an index. We go to that index in the bit string and we set that bit to indicate membership of the set. And then obviously we can go and query that membership in the same way. Obviously we have basically an infinite possible set of strings and URLs that could be inserted, and we only have this fixed length bit string, so it's there is false positives, and it's basically a probabilistic set method. So to actually distribute this data amongst Tor browser users, our idea is that this can be actually distributed amongst the consensus that already exists in Tor. So every Tor client or Tor browser client will periodically retrieve the Tor consensus from guard nodes or directory authorities, and it would be quite sensible for us to kind of piggyback off that and have users get their up-to-date HSTS data from that system. So if we want to actually load a website in this protocol, first of all, when we decide we want to visit a website, we have to go to our local Bloom filter and check if the website is present, and that'll indicate whether it should have HSTS or not. If it does have HSTS, we connect to the website and we assume that we must have a HTTPS connection. If there is no HTTPS available, we can't connect to the website, we block it, because there is likely to be some kind of SSL downgrade attack happening, and we don't want that. But regardless of whatever happens here, if that website reports HSTS to us then when we load it, we then have to report this back to the system through the guard nodes or directory authorities. So the protocol also has privacy guarantees that come from the Rapport protocol. So if we have a bit string like this, which is our submission to the system, this of course would indicate which website we're visiting, so we don't want to reveal that to others. So as the Rapport protocol works, it has privacy parameters key and q, which basically are the probability that any zeros get perturbed into ones and any ones get perturbed into zeros. And so we have local differential privacy in that way. So the way the protocol is set up so far, it actually is very vulnerable to denial of service attacks. So basically any malicious user could simply submit loads of submissions on loads of different websites to falsely claim that these websites should have HSTS. And that would mean that users would be blocked from visiting any legitimate non-HTTPS websites, which we don't want. So to actually mitigate this denial of service, not only do we report websites that have HSTS, we also report websites that don't have HTTPS. And this allows us to mitigate these denial of service attacks. So in this improved scenario, we have two Bloom filter data structures we store, so the HSTS Bloom filter and the non-HTTPS Bloom filter. So when we want to access a website, we decide which website we want to visit. We first check in the first Bloom filter, does the site appear to have HSTS? So in this case, if it is present, we attempt to load the website. If we get a HTTPS connection, that's great, no problems. But if we don't get that HTTPS connection, initially we can assume, okay, there must be an SSL stripping attack happening. So that's bad, we don't want to connect to the website. But before we make sure, we just want to check in the other Bloom filter, has the site been reported as not having HTTPS? And if the site appears in both Bloom filters, this means we kind of have a contradiction, because a website can't have both HSTS and also not have HTTPS. So in this case, we know that basically there's been a kind of breakdown in the protocol. It could be a false positive, or it could be some kind of denial of service attack. But in this case, we don't, we basically don't block the user from accessing the website. So it's not the user won't be left any worse off, basically, as a result of using the protocol. And we avoid denial of service attacks from actually stopping the user from visiting legitimate websites. So to actually check the kind of effectiveness of the protocol, we conducted a lot of simulations. And basically we take a number of different inputs to kind of see how the website would be, or the protocol would be set up. So the first one is the number of actual submissions that get put into the protocol on a day-to-day basis. For this, we basically estimate that, imagine this protocol was used by every Tor browser client. And so we take the number of daily Tor users as a rough estimate of the number of websites that could be submitted. This is a conservative estimate because we're assuming every Tor browser user only visits one website every time they use it. Then we take the desired levels of differential privacy epsilon as an input, and then the estimated percentage of current HSTS and HTTPS deployment on the web, and finally the acceptable ratio of basically false positive results to true positive results. And so from running these simulations, we get two outputs. We get the desired Bloom filter size, which is something that can kind of periodically adjust as the protocol runs. And we get the maximum number of modeled sites, which I'll discuss a bit more about in a moment. So first of all, simulating the Bloom filter size. So we can see we have 3 different sample differential privacy epsilons that we've produced here. And we can see that as the Bloom filter size increases, we kind of get better results up until a point after which it kind of declines. So basically this is we can select here kind of an optimal Bloom filter size for the protocol. And this is, as I said, a process that will have to kind of rerun if this protocol is deployed in the wild, periodically rerun to kind of adjust this Bloom filter size as necessary. And then, as I said, we simulated the number of websites that we could model. So basically here, basically any number of possible websites that could be submitted to this protocol is infinite. It's the set of all possible strings, basically. So we can't actually fully model that. We can only get an estimate, and we want to here see the maximum number of sites that can be modeled. And basically, the bigger that number is, the more confident we are that this protocol would work well in the real world. And so you can see as the numbers go up, at some point the effectiveness, the true positives, will drop to 0, and that's because the input that we had of the acceptable ratio of false positives to true positives has gone too high, and at that point we say that the utility has gone to 0, so we kind of assume we can't go any further than that. So just for example, if we have differential privacy of 7 here, epsilon of 7, we can get up to around 100,000 websites modeled. And basically our argument is that although it could be an infinite number of websites submitted, 100,000 is kind of a good enough estimate that we can say that the majority of websites that will be visited on a day-to-day basis by Tor browser users should be present in 100,000 possible websites. So it's kind of our hope that that is sufficient, basically. So to conclude, the protocol CoStricTor provides crowdsourced HSTS data for Tor browser, and we can accurately report on 100,000 websites with a reasonable level of false positive results. And this will, of course, improve with increasing HTTPS adoption and HSTS adoption, which has kind of been constantly growing over the past number of years, and also with increasing numbers of Tor browser users as well. And not only does it provide HSTS for websites which generally should have HSTS, it also kind of accidentally also upgrades or forces HTTPS on other HTTPS websites. So it kind of gives you an extra protection in other circumstances as well. And this, of course, reduces man-in-the-middle attacks on Tor browser and just increases the general safety overall. And there also is, you can ask me about later, a method of actually using this protocol to help identify more malicious exit nodes on Tor, which is also always a good thing. And that's it. So thanks very much for listening, and I'll take any questions.
Thank you, speaker.
Yes, thank you very much for the talk. I was wondering about your Bloom filters. So you have two of them. Do they both use the same hash function?
Yes.
Okay.
Yeah.
And what is it, if I may ask?
So there's a couple of different choices. They're not usually they're not cryptographic hash functions.
Okay.
They don't need the same properties, but they're kind of the only properties it needs to kind of have a distribution of numbers that could, I can't remember the exact phrase, but yeah.
Okay. Yeah, I was just thinking about could I try to strategically try to set some bits to manipulate stuff, but
I think it would be difficult because one of the things is that you need a sufficient level of submission. So you can't just put in one submission and change how the output works for users. There has to be a number of submissions from different people to kind of make changes in the output data.
Thank you.
Thank you. Yeah, this is very interesting. My only question is, it seems like it's a binary thing, like HSTS or not HSTS, but as far as I recall, right, there is a max age in the header. Do you account for that in any way?
Yeah, so there is basically a way of tolerating expiry time, which is in the paper, but I didn't have time to get into here. So basically, the protocol works in kind of epochs, which we can arbitrarily say it to be like a month or something. So we actually store data from the previous month and the current month, and then we kind of periodically drop off the previous month's data. So month by month, if websites aren't resubmitted to the protocol, that data will be removed. So it doesn't exactly equate to the expiry times that HSTS uses, but it kind of it gives us some implementation of that feature, basically.
Other questions?
So how do you compare your design with a much simpler design for just have a preload version of all the HSTS website and just shape that thing within Tor browser, or maybe just download that after Tor browser have connected to Tor network?
So this is so in HSTS there is this idea of the preload list, which is this list of websites that you can submit as a web administrator. You can submit your website to this to say that you have HSTS, and that will actually be distributed with all web browsers. This is an issue with people actually using it, so not that many website administrators actually submit their website to the preload list, and it also kind of loses the ability to expire your website. So if you put your website on the preload list, for example, it must stay there for quite a long time, basically. It's very hard to remove. So I think, if you had some kind of similar construction of having a list of websites that always have HSTS, you kind of have issues there with expiry, and how do you get your website off the list, basically.
I'll ask one last question while James gets set up. Did you calculate the communication overhead costs?
Yes. Basically, I can't remember the number off the top of my head. I think basically it's on the order of kilobytes is the bloom filter size for the simulations we did. So overall, it's not too much extra traffic in
Kilobytes per client, right? Per
Yes.
fetch.
But this will only occur when you're fetching the consensus, basically. So it's basically an extra few kilobytes on top of the consensus.
Okay,
And so it doesn't have to, there's no network overhead on every fetch, basically.
gotcha.
That makes sense.
All right, let's thank the speaker again.